Hi everyone, I am Praharsha. Today I'm going to discuss how AI is used in autonomous vehicles. Let's start from the scratch. In simpler terms, what AI is. When a machine completes tasks based on a set of rules that solve a problem, such intelligent behavior can be mentioned as AI. Machine learning and deep learning are ways to create or train AI. Deep learning is a subset of machine learning or the next evolution of machine learning. Deep learning is inspired by information processing patterns found in a human brain. It leverages complex neural networks that extract more detailed features as the neural networks continues to learn and evaluate its input data. There has been a lot of buzz about the autonomous vehicles in recent years is due to the surplus of data available now. In this slide, we're going to discuss how does AI work in autonomous vehicles. AI-based systems will become a standard in new vehicles in these two categories. Infotainment human-machine interface, including speech recognition and gesture recognition, eye tracking and driver monitoring, virtual assistants, and natural language interfaces. Advanced driver assistance systems and autonomous vehicles, including camera-based machine vision systems, radar-based detection units, driver condition evaluation, and sensor fusion engine control units. Autonomous vehicles are equipped with multiple sensors such as cameras, radars, and lidars, which will help them better understand the surroundings and in the path planning. These sensors generate a massive amount of data. To make use of the data produced by these sensors, autonomous vehicles need a supercomputer like whose processing capabilities are very high. Companies developing autonomous vehicle systems rely heavily on AI in the form of machine learning and deep learning to process vast amount of data efficiently and to train and validate their autonomous vehicle driving systems. In this slide, I'm going to talk about AI perception action cycle, which is created when the autonomous vehicles generate data from its surrounding environment and feed it into intelligent agent, who in turn makes decisions and enables the autonomous vehicle to perform specific actions in the same environment. The figure the figure below illustrates the data flow in autonomous vehicles. There are mainly three components. The component 1, in-vehicle data collection and communication systems. The autonomous vehicles are fitted with numerous sensors, radars, and cameras to generate massive amounts of environment data. All of these form the digital senses, through which the autonomous vehicle can see, hear, and feel the road, other vehicles, and every object near the road, just like a human driver would pay attention to the road while driving. This data is then processed with supercomputers, and data communication systems are used to securely communicate valuable information to the autonomous driving cloud platform. The autonomous vehicle first communicates the driving environment and the driving situation to the autonomous driving platform. Now, the second component, autonomous driving platform, which is like a cloud. The autonomous driving platform, which is in the cloud, contains the intelligent agent which makes use of AI algorithms to make meaningful decisions. And the next component, AI-based functions in autonomous vehicles. Based on the decisions made by the intelligent agent, the autonomous vehicles can detect objects on the road, maneuver through the traffic without human intervention, and gets to the destination safely. Autonomous vehicles are also equipped with AI-based function systems such as voice recognition, gesture controls, and few more. These functions are carried out based on the decisions made by intelligent agent in the autonomous driving platform. The driving experiences generated from every ride is recorded and stored in database to help the intelligent agent make much more accurate decisions in future. The data loop called perception action cycle takes place repetitively. The more the number of perception action cycle takes place, that much more intelligent the intelligent agent becomes, resulting in a higher accuracy of making decisions, especially in complex driving solutions. In this slide, I will talk about the main tasks of any machine learning algorithm in self-driving car is a continuous rendering of surrounding environment and prediction of possible changes to those surroundings. These tasks can be divided into subtasks like object detection from the sensors and cameras as we get the data. So once after we get the data, we can use clustering like k-means and multi-class network multi-class neural networks to classify them. The second one will be like identifying the object and classifying them. We can use like SVMs, KNN, and PCA to classify the data. Object localization and prediction of the movement. The regression models like neural network regression and Bayesian forest regression are used for prediction of the movement. A detailed explanation will be given in the coming slide about each task and the corresponding ML model which can be used. In this slide, I'm going to talk about the machine learning algorithms that can be implemented for the tasks mentioned in the previous slide. The first one being the regression algorithms. In advanced driver assistance systems, images play a very important role in localization, while the biggest challenge for any algorithm is to develop an image-based model for prediction and feature selection. The type of regression algorithms that can be used for self-driving cars are Bayesian regression, neural network regression, and Bayesian forest regression, among others. The next one being pattern recognition algorithms like classification models. In advanced driver assistance systems, the images obtained through sensors process all types of environment data. Filtering of the images is required to recognize instances of an object category by ruling out the irrelevant data points. Pattern recognition algorithms are good at ruling out unusual data points. Recognition of pattern in dataset is an important step before classifying the object. These algorithms can be defined as data reduction algorithms. These algorithms help in reducing the data set by detecting object edges and fitting line segments and circular arcs to the edges. Line segments are aligned to the edges up to a corner, then a new line segment is started. Circular arcs are fit to the sequence of line segments that approximate an arc. The image features are combined in various ways to form the feature that are used for recognizing an object. The support vector machine with histograms of orient gradients and principal components analysis are the most common recognition algorithms used in ADAS. The next being the clustering. We can use k-means clustering or multi-class neural networks to do the clustering analysis. What happens is sometimes the images obtained by the system are not clear and is difficult to detect and locate objects. It is also possible that classification algorithms may miss the object and fail to classify them. The reason could be low resolution images or very few data points. This type of algorithm is good at discovering structure from data points. Clustering methods are typically organized by modeling approaches such as centroid-based and hierarchical. All the methods are concerned with using inherent structures in the data to best organize the data into groups of maximum commonality. If you see the example image over here, we can actually group, we really cannot classify them as it is as the image is not clear, but still we can group the image with other images which are very similar to this and make a correct decision. Coming to the next, decision matrix algorithms. This type of algorithm is good at systematically identifying, analyzing, and rating the performance of relationships between set of values and information. These algorithms are mainly used for decision making. Whether a car needs to take a left turn or it needs to brake depends on the level of confidence the algorithm have on the classification, recognition, and the prediction of the next movement of objects. The algorithms are models composed of multiple decision models independently trained and whose predictions are combined in some way to make overall prediction while reducing the possibility of errors in decision making. These algorithms use gradient boosting and ADA boosting. In the coming slides, we'll go through the autonomous car project implemented by NVIDIA using the convolutional neural networks. From here on, all the discussion will be how NVIDIA was able to develop an autonomous vehicle using convolutional neural networks. Initially, a convolutional neural network is trained to map raw pixels from a single front-facing camera directly to steering commands. This end-to-end approach proved surprisingly powerful. With minimum training data from humans, the system learned to drive in traffic on local roads with or without lane markings and on highways. It also operates in areas with unclear visual guidance, such as in parking lots and on unpaved roads. The system automatically learns internal representation of necessary processing steps, such as detecting useful road features with only human steering angle as a training signal. We never explicitly trained it to detect, for example, the outline of the roads. Compared to the explicit compositional problems such as lane marking detection, path planning, and control, our end-to-end system optimizes all processing steps simultaneously. Let's start with what a convolutional neural network is. It is a deep learning algorithm which can take in an input image, assign importance to various objects in the image, and be able to differentiate one from the other. The pre-processing required in convolutional net is much lower as compared to other classification algorithms. While in primitive method filters are hand-engineered with enough training, convolution nets can learn these filters. The architecture of a convolution net is analogous to that of a connectivity pattern of neurons in human brain and was inspired by the organization of the visual cortex. To understand how these layers work, it's important to first understand the concept of convolution. Convolution is officially defined as an integral that shows the amount of overlap of one function and is moved across the other function. As this is a project undertaken by NVIDIA to create a autonomous car using convolution neural networks, they are getting their own data train, to train the model by using a drive-by-wire test vehicle. Training data was collected by driving on a wide variety of roads and in a diverse set of lighting and weather conditions. Most road data were collected in central New Jersey, although highway data was also collected from Illinois, Michigan, Pennsylvania, and New York. Other road types include two-lane roads, residential roads with parked cars, tunnels, and unpaved roads. Data was collected in clear, cloudy, foggy, snowy, and rainy weather, both day and night. In some instances, the sun was low in the sky and resulting in a glare reflecting from the road surface and scattering from the windshield. And next, we're gonna talk about the network architecture, that is the convolution neural network architecture. So the network consists of 9 layers, including a normalization layer, 5 convolution layers, and 5 fully connected layers. The input image is split into YUV planes and passed to the network. In this slide, we're going to talk about how training and architecture of CNN is done. The image one tells how neural networks are trained. Images are fed into convolution neural networks, which then computes a proposed steering command. The proposed command is compared to the desired command for that image, and the weights of the CNN are adjusted to bring the CNN output closer to the desired output. The weight adjustment is accomplished using the backpropagation. Coming to the architecture of CNN, the network consists of 9 layers, including a normalization layer, 5 convolution layers, and 3 fully connected layers. The input image is split into YUV planes and passed to the network. The first layer of the network performs image normalization. The normalizer is hard-coded and is not adjusted in the learning process. Performing normalization in the network allows the normalization scheme to be altered with the network architecture and to be accelerated via GPU processing. The convolution layers were designed to perform feature extraction and were chosen empirically through a series of experiments that varied layer configurations. The 5 convolution layers with the 3 fully connected layers leading to an output control value, which is the inverse turning radius. The fully connected layers are designed to function as a controller for the steering. For the convolution neural networks to make a decision, it needs to classify the image. For that to happen, it needs to use image recognition. The image detection plays a crucial role in classifying the object. Here, the convolutional part of the network refers to a representative kernel being moved across a given image. A kernel is a matrix of values created to detect different features. For example, you may have a 3 by 3 kernel which is assigned 9 separate values. These values are assigned so that the kernel has specific function. This kernel is then successively centered on each pixel of the image. As the kernel is iterated across the image, the inner product of the kernel and the overlapping image is calculated, and that value is assigned to the corresponding pixel. This value is a measure of similarity between the input image and the kernel. In autonomous vehicles, the kernels are designed to detect specific features such as edges. When the convolution reaches a local maximum, that position is classified as an edge. Even within edge detection, different kernels are needed. Depending on their values, kernels can be used to detect differently oriented edges. The filtered images are fed into next layers, which determines which parts of the image has potential obstacles. A pooling layer is thus a way to focus the CNN on regions which contains potential obstacles. Fully connected layers usually come at the end of the network to condense the data to one final output. Fully connected layers function similarly to convolution layers in that they both produce inner products. However, every neuron is fully connected layer is, is connected to every output of the previous layer, whereas in the convolution layers, neurons are connected to a group of outputs. This means the fully connected layer analyzes all the data points simultaneously without performing a convolution function. For example, if we look at this image, we use this image by the autonomous car for obstacle detection. Here, the image recognition is not as easy as it looks. The machine must be able to recognize metric, symbolic, and conceptual knowledge. Metric knowledge is the identification of the geometry of static and dynamic objects. This is required to keep the vehicle in its lane and a safe distance from other vehicles. Symbolic knowledge allows the vehicle to classify the lanes and conform to basic rules of the road. Conceptual knowledge allows the vehicle to understand relationships between traffic participants and anticipate the evolution of driving scene. Conceptual knowledge is the most important aspect for being able to detect specific objects and avoid collisions. In this slide, we're going to see how learning in CNN is done. The convolution neural networks learn using stochastic gradient descent and backpropagation. The goal is to make predictions of the CNN match the ground truth by minimizing a cost function. To train a CNN, it must be run in both feed-forward and feed-backward configuration. Over the forward run, small errors are collected and analyzed by the loss layer. The cost shows the margin between what the CNN recognizes and the ground truth is. The error is minimized using the stochastic gradient descent. Stochastic simply means the training images are fed through the network in small and random subsets. A subset method is better than feeding a whole set at once because it allows for the variety in what the network sees. If the images were not fed in subsets, the network would only be able to identify images in a specific configuration of the training set. Gradient descent is the more complex part of the process. It uses a loss function mentioned here. In this equation, y of x represents the desired output and a is the output of the network has provided. As you can see, the closer a gets to y of x, the smaller the cost of c. Gradient descent is the algorithm used to find the collection of weights and biases that will allow c to reach its minimum value. The main idea behind the gradient descent algorithm is to find the gradient of the function to be minimized and move the values of the variables in the opposite direction so as to guarantee the gradient will always be decreasing. Once the model is trained and built using the training data, rather than directly taking the on-road test, the NVIDIA company has done a simulation where they initially tested the car on a simulator for the performance, where it showed a really good performance in the simulator, and later on they loaded the same CNN model onto the Drive PX module, which is created by NVIDIA, to fit into the car. So once this is done, they went on to on-road tests where The car was autonomous approximately 98% of the time, and it almost drove like 10 miles with zero intercepts. So here, what is autonomous is the estimation of what percentage of the time the network could drive the car. This metric is determined by counting simulated human interventions. If, for example, if there are zero human interventions, means it's like totally the car is totally autonomous of the whole time. So I'll be concluding by saying it will be revolutionary if we are able to generate a level 5 autonomous car and put that into real world production, but at the same time we should be considering all the possible scenarios before bringing them onto the roads. So these are the articles where I referred to prepare this presentation. Thank you for your time.